to discuss the most important trends in the world of AI, and the talks are live-streamed and viewed around the entire globe, helping to spread the word about amazing work going on in the AI community. I would like to thank Dean Jelena Kovacevic, as well as my own Department of Electrical and Computer Engineering, for supporting the series and graciously hosting our esteemed speakers, all of whom are world-renowned experts whose research is making an immense impact on the development of new machine learning techniques and technologies. In the process, they are helping to build a better, smarter, more connected world. I'm proud to have here today Francis Bach of INRIA, the French National Research Institute for the Digital Sciences. Since 2011, he has led its machine learning team, which is part of the computer science department at École Normale Supérieure. Francis has been called one of the best researchers of his generation in the domain of machine learning and its applications, and I will begin by giving you a little background on his path to earning that impressive reputation. He graduated from École Polytechnique in 1997 and completed his PhD in computer science at UC Berkeley in 2005. It was at Berkeley that he began exploring machine learning for the purpose of developing automated processing methods, the only methods capable of handling the complex and increasing amounts of digital data now being generated. He next spent 2 years in the mathematical morphology group at École des Mines de Paris, and in 2007 he joined the computer vision team at INRIA, remaining there until assuming his current role. Francis' primary interest concerned machine learning, especially in sparse methods, kernel-based learning, large-scale optimization, computer vision, and signal processing. His work in those areas has earned his multiple European Research Council grants, the 2012 INRIA Young Researcher Prize, the 2014 International Conference in Machine Learning Test of Time Award, the 2018 Lagrange Prize in Continuous Optimization, and the 2019 Jean-Jacques Moreau Prize, among other honors. He has served as chair of the International Conference in Machine Learning and now co-edits the Journal of Machine Learning Research. Before the PhD, the high-level research, the industry laurels, however, his journey started, or so I've read, when he was given a backgammon set. He became intrigued with figuring out the game, especially the mystery of how an algorithm could be used to beat world champion players. Although at the time he could program only using C language, he dove into the scientific literature, and career was born. Francis will be speaking today on distributed machine learning over networks. He explains that distributed systems are the common way to process more data than one computer can store, but they can also be used to increase the pace at which models are trained by splitting the work among many computing nodes. He'll discuss with us the corresponding problem of minimizing a sum of functions that are respectively accessible by separate nodes in a network and the process of developing optimization algorithms for this particular class of distributed optimization problems. Perhaps if we are lucky, he might also share some tips for winning at backgammon. Now, without further ado, let's welcome him to the stage.
So thank you, Anna, for the very generous introduction and for the invitation to come here today in such a nice place. So today I'm going to talk about joint work with colleagues, and I would like to highlight the contributions of Kevin Scamon, who was a postdoc in the lab, and of Adrien Hendricks, with a student, PhD student at INRIA, and also Laurent Massoulier at INRIA, and Sébastien Bubec at MSR in Redmond, and Dean Tatley now at the University of Washington. So this context is very clear for this talk. So there is more and more data to process in all areas. So beyond Google and Facebook, there is a lot of sciences in dire needs for automated ways of dealing with data, from bioinformatics to humanities. And in recent years, faced with this need of processing data automatically, machine learning has been a key component. And you can attribute the success of machine learning in recent years by a combination of several factors. First, models. So there are like specific models for every type of data. Algorithms to treat those models, lots of data to learn from, and to treat those large data sets, a lot of computing power. So this is commonly admitted that the success is due to those four elements. And now if you want to go further, and in particular if you want to go further in terms of computing power, since Moore's law is starting to reach an end, there needs to be something to be done beyond having a faster computer. And one way of doing it is to have multiple computers or multiple processors, multiple nodes, And this is the goal of the talk today, is to explore algorithms that can leverage the computing power coming from several nodes. Since those computing nodes have to be like somewhere, and they have to be connected, and hence the network aspect. So today the goal is how can we leverage multiple computers to still be faster and treat even more data. So this will be the outline of my talk. The first part will be like reviewing what I mean by machine learning. Essentially, I will view this through the lens of optimization. You want to minimize the training error, which is a finite sum over the entire data set. And I will present what are now the optimal algorithms for single machine optimization, and optimal with quotes because it's always optimal with respect to a certain model, and I will explain that, what I mean by that. And then I will move forward to the optimization of functions which are defined over a network without any machine learning, component. And also I will present optimal algorithms, again, optimal for a certain model of computation. And finally, I will bring things together in the last part of the talk where I will try to distribute the algorithms that I've presented in the first part to get, if possible, fast improvements, strong improvements, even if you go from 1 to 2 machines, and if potentially many more. So to set things up, I will consider the classical parametric supervised learning problem with n observations, xi, yi. Xi can be an image, yi can be a label on that image, and I'm going to predict y given x through some prediction function, h, which takes inputs x and some parameter theta. And I'm going to assume that the parameter theta is quite high dimensional. So there are two main classes of prediction functions that people consider. The first one are linear models, and this is like used a lot, in particular in advertising, where you receive a big sparse vector of zeros and ones for every client. So it's indexed by the websites. I'm caricaturing a bit, but you see what's happening. And for every website, you have a 1 if you went there and a 0 otherwise, and you combine them linearly to predict if you're going to click or not on some ad. Okay, so this is typically in the high dimensions when D and N are very large. So in this talk, D will always be the dimension of the underlying space, and N will be the number of observations or the number of machines later in the talk. So this is easy for us in terms of understanding because of the linear model. However, if you want to work like on images or on language, there are other types of models. So here, the task of separating dogs from cats. And neural networks are being used, and they move away from linear models. Okay? Instead of building a feature vector which is like high dimensional and then combining linearly the components, there is like a sequence of linear maps plus some nonlinear activation function, which is iterated, okay, and leading to the term deep learning when you have many such layers. So for us optimizers, this is much harder because it's not anymore linearly parameterized, and this will lead, as we showed in a moment, to non-convex problems, whereas linear models were leading to simpler convex problems. So how is it trained? This is trained by trying to minimize some cost function, and typically defined as the average over some training data of some loss, okay, between what I want to predict, yi, my label, and my prediction function, plus some regularizer to avoid overfitting. So if you want to know what the loss is, you can imagine this is a least squares. Okay, this is used a lot when y is a real value. And if y is some binary variable, then people typically use logistic regression, and this is a formula over there. So the talk is not robust, but it's, we don't care so much about the loss as long as the loss is convex in H. So this is a weak assumption, as most losses that people use in practice are convex. All right, so one side note, so this talk focuses only on optimization, okay? So trying to minimize the training error plus some regularization. But clearly, this is just a mean to an end. The goal is to really do well on test error. I could give the same talk with test error in mind, but that would be for next time. So today is only like a training error, but keep in mind that this is just not what you care about at the end. So what makes machine learning special, okay, is that we optimize not any cost function. So for a while, up to maybe 5 to 10 years ago, people would use like classical optimization algorithms which were not dedicated to machine learning. But now people have realized, it's not me, it's many people, that if you leverage the finite sum structure of our function, you can do many good things. So this is really the topic of the talk, is that all the functions that we care about in machine learning happen to be finite sums. So as I mentioned already, there are two classes of problems. There is the convex problems, and for machine learning, since I'm assuming some convex laws, this corresponds to linear models. And you have some non-convex problems, which correspond essentially to neural networks or other nonlinear prediction functions. So in this talk, I'm going to focus mostly on convex models because I want to get guarantees, but noting that for half of the algorithms I'm going to present, we don't need convexity to define them. We just need convexity to get any form of guarantee, so you can still try on non-convex problems. At the end of the talk, I will describe algorithms which do require convexity to be defined, and I'll talk about that later also. All right, so now what are the classical algorithms when you're faced with a finite sum? Okay, so here, for this slide, the finite sum, every component of the finite sum is simply the loss on a single data point. It could be a mini batch as well. So the classical thing is first to use a batch gradient descent, where you go down the negative gradient of your cost function. It's a very old algorithm dating back from Cauchy in the 1800s. And so what is known about this algorithm, at least in the convex case, is that it does converge reasonably fast, okay? In fact, exponentially. And the time constant that is characterizing how fast you're converging is often called the condition number, which I denote kappa over there. And it's not a talk about condition number, but essentially the condition number will tell you how your function looks locally. So you have a low condition number if your level sets looks like round balls, and you have a high condition number if they are elongated ellipsoids. And more formally, this is the ratio between the largest eigenvalue of the Hessians over the smallest eigenvalues of the Hessians. For this talk, you can see kappa as being equal to n. Okay, so essentially, for machine learning, as you get more data, the condition number tends to increase, and there are several arguments to show that this is of the order n. So whenever you see kappa, you imagine that kappa is n or larger. So what has been known is that so this condition number does characterize convergence, and this can be accelerated. Okay, so when n is 1 billion, okay, so going from n to square root of n is a strong gain. This is a Nesterov acceleration, which is very important for optimization. The issue, however, is that whenever you have to make a step, you have to compute the full gradient, which is over there, which is composed of the average of all the gradients of all of the individual functions. And this is costly, so you have to make a pass over the data at every iteration. So you pay per iteration O of nd. Every iteration can be making a lot of progress, but at the end, you need to make each of them is very costly. So this has led to stochastic gradient descent. So as a side note, it is not a descent technique. It may go up once in a while, but this is the way it is called. And you replace the full gradient like this by just selecting a single function at random, okay, which is here I of t, which you select uniformly at random on the set 1 to n. So by design, every iteration is non-costly because you have like independent of n at every iteration, but you lose this exponential convergence to get something of the form 1 over t, which is much slower. Still, the condition number is appearing. Right, so what has been the progress in the last 15 years? 10 years, a bit less, is the design of new techniques which will have the best of both worlds. Exponential convergence with a very precise rate of convergence, but also an iteration cost which is independent of n. So this started with my postdocs, Nicolas Leroux, then postdocs, Nicolas Leroux and Mark Schmidt, and then it has been followed up by a series of work which go like this. So this is the stochastic gradient. What you can see that if, so here it's random, it's a random algorithm because I'm selecting functions randomly. So here, given the past, the only randomness is the selection of my new function. And if I take the expectation of this with respect to it, I get the average of all functions. So I get the full gradient of the problem. So we see that the stochastic gradient is unbiased, but the issue is that it has a very strong, very large variance. And the variance does not go to 0 as I make progress. And given this like unbiased estimation with a strong, big variance, then people have designed ways of reducing variance. Okay, and this is classical in Monte Carlo methods to add some terms to reduce variance, and this is essentially what's happening. So it was not cast this way at the beginning, but I think it's a very nice contribution of Johnson and Zeg and colleagues to highlight the fact that those techniques were in fact doing variance reduction. And at the end, what they do, they're going to store some values of the previous gradients, and with the idea that you preserve unbiasedness. So here, if you store some value yit at time t-1, okay, and if you add the average of the values and you subtract the same random value as this one, then you preserve you preserve unbiasedness because the expectation of this is equal to that. But if the gradients are highly correlated with this one, then you do have some variance reduction. And this is essentially what has been done in the last 5 or 6 years. So here, details do not matter so much. What matters is that it's a very simple algorithm, still like 1 or 2 lines of code. And the good thing about those algorithms is that they can be analyzed very precisely. Okay, so here, give me, let's say, a logistic regression. Then I can, a priori, before I even see the data, or after I see the data with only a few statistics, I can tell you how much, how fast it will converge. So this is what is presented in this slide. If you want to reach precision epsilon, however, okay, there are many ways of defining what I mean by precision, but any would work. Then this is the time it takes to reach precision epsilon. Remember, kappa is still the condition number of order n for machine learning. So this is like the 2 classical techniques, so SGD, okay, which does not convert exponentially fast, hence the dependence which is not logarithmic in the precision, whereas all other techniques do converge exponentially fast, leading to some logarithmic factors in terms of the precision. The key here is that SGD, since every iteration has a complexity which is independent of n, then n does not appear in the complexity, whereas for gradient descent, it does appear. So with gradient descent, you gain in terms of the logarithmic dependence, but you lose in terms of the dependence in n. So what those variance reduced techniques are allowing ourselves to do is to replace the product essentially by a sum. And so when kappa is of order n, the gains are quite significant. And this is a gain in theory, and I will show gains in practice later in the talk. Okay, so here, those are precise convergence rates which are made available because we assume convexity of the problem. Important aspect, this can be accelerated. Okay, so by using a very similar technique than Nesterov acceleration, you can replace the sum n plus condition number by another formula. When kappa is n, this does not bring any benefits, but when you get very ill condition problems, this starts to be important. One other very nice aspect of this line of work, and when I mean this line of work, it's mean like by many people, not just by us, is that now they are matching upper and lower bound of complexity, meaning that if you allow yourself to minimize the finite sum and you have access to gradients 1 by 1, okay, and you only combine linearly those gradients, you cannot improve over the complexity, over this complexity. So this means that essentially for a single machine optimization, this is up to constants the best algorithm if you, of course, only combine gradients linearly. All right, so this is like the state of the art for single machine optimization in the convex case. Let's now move to distributed optimization. All right, so now I'm going still to minimize the finite sum, but big difference is that not the finite, every element of the finite sum can be anything. Okay, later on in the talk, this will be like some learning, some testing, a training error on some data set. But for the moment, for this like second part of the talk, I'm going to assume that I have a set of functions, okay? Each function is attached to a node in a network, okay? So here a network with 9 nodes. And the rules of the game, because I want to provide both upper and lower bound of complexity, so I have to decide what my algorithm is allowed to do. And what are we allowed to do is that each node can access only its own function, its own gradients, but is allowed to communicate vectors to its neighbors. Okay, so node 5, for example, can access F5 and communicate once in a while nodes, the vectors to node 3, node 6, or node 7. So why do you care about that? So for several reasons. As I've mentioned earlier in the talk, you want to leverage computing power for 2 reasons typically, either because your data set is spread over the globe, and this was the motivation when we did that work with Microsoft. So if you're here, if this is New York, this is Florida, this is, let's say, Redmond, and you have several data centers, and you want each of them to learn a global model, but with no exchange of data. You may exchange parameters, but not data. So this is one reason. data are spread over like a network, and I don't want to exchange data points. Other aspect is I'm allowed to share data, but I want to benefit from more power. Okay? If you have multiple cores in a machine, this is typically what ends up appearing. So here, as soon as you have a network, we start to have some constraints. Okay, so first we're going now not only to minimize the time it takes to compute gradients, which was the main limitation factor when we had a single machine, but now we want also to minimize the communication costs. So now the goal is to be optimal both with respect to communication and with respect to local computation. Right, so the first thing you may think of, and whenever you go from a single machine to multiple machines, why not distribute the simplest and best algorithm on a single machine? So here, if I make no assumption regarding like machine learning, the best I can do when I have a convex function is to do Nesterov acceleration. And maybe I can simply just take Nesterov acceleration, which is just gradient descent plus some extra momentum terms, and try to see if I can distribute it over a network. So essentially, since my gradient is a sum of gradients, what I need to do if I want to implement this gradient descent over a network is to be able to do network averaging. So if every node here has some value, let's say a gradient of its own function, I want to be able to share that value with the rest of the network. So it's essentially computing the average of values in a network. So this will be the first task we're going to tackle, the simplest ever optimization task on the network, which is essentially computing some averaging. So now I give you n values, xi1 to xin. So those are real numbers, but you could imagine they could be gradients in dimension d. That would just make my slides a bit more complicated, but everything works the same. And the goal is to compute the average of those values, which is known to be a minimizer of the square deviation with respect to theta. Okay, so as you can see, computing an average is really the simplest possible task if you have a network. So for this, there are two types of algorithms. First, centralized algorithms, where the idea is that you have a master node that can give orders to the other nodes. And typically, the best you can do in that setup is you take your graph over there. You first build a spanning tree over that graph, and this can be done with a cost of a factor of 2 in terms of diameter. So if I start with a graph of diameter delta, I can build a spanning tree with diameter of 2 delta. Okay, so I'm going to pay such a price. And then if I want to do averaging, what I'm going to do, I'm going to, every node will send its values, okay, to a master node. So here 4 is declaring itself as a master node. And simultaneously, 8 will send something to 9, 7 will send something to 5, then second round, 5 will send something to 6, 9 will send something to 6. And like if you do this, like going from the leaves of the node, the leaves of the graph to the root here 4, you end up with a number of steps which is proportional to the diameter of the graph. Okay, and here what's important is the fact that at every time step, several nodes are allowed to communicate simultaneously. And at the end, you end up with 4 with the exact average, okay, and with no errors. Okay? The key here is that this centralized averaging algorithm, which is very, very classical, does not make any errors. So you get the exact average. So if you use this within optimization to both send the common vector of parameters theta, and to average gradients, then you end up having an optimal algorithm. So what I mean by optimal about the class of algorithms that are allowed to, as I mentioned, compute gradients locally and exchange vectors with the neighbors. And what is this complexity? Is simply the number of gradient steps is the same one as for Nesterov acceleration. Okay, so I want to optimize the function with condition number kappa. I cannot do better than this. Okay, and in terms of communication steps, the ones I have described at the moment is whenever I compute a gradient, I need to do network averaging, and this was done with delta communication steps, delta being the diameter of the graph. And this turns out to be optimal. So there are, you cannot beat this if you're allowed only to follow the rules that I have set up. So here, as you can see, when you do network optimization, there are always two quantities that will characterize the problem. One only based on optimization, kappa. So I have a function g which I want to minimize. Regardless of networks, the best I can do will depend on kappa. and a quantity which is based on the graph itself. So if I have a graph which has a small diameter, like a star, things will be easier than if I have a graph with a long diameter, like a chain. Okay, so this will always be the case throughout this talk. If you want to consider network averaging or network optimization, you have to have two quantities, one based on optimization and one based on the graph. All right, the question is, when you have a centralized algorithm, is that they have some robustness issues. Okay, so this is very classical. So if in that graph, after I form the spanning tree, one node goes down, so if 6 goes down, then I will lose the entire contribution of this right part of the graph. Even worse, if the node 4 goes down, so here my master node, it's even worse. So this is why researchers have considered algorithms which are not centralized anymore, which are called decentralized, and this will be the main topic of the remainder of the talk. So to doing this, there are many frameworks to do that. I'm going to follow the gossip framework of Boyd and colleagues, where the idea is that at some time, some node will wake up, let's say node 4, and will ask the value of its neighbors and average those values. Okay, so here, if I is 4, I replace the value that I had in my node by the average of those values. So this corresponds to do linear. Okay, so W will always have typically positive values and only give contributions to neighbors in the graph. What is nice about this algorithm is that it can be totally asynchronous in the sense that nodes can wake up at different times and ask values of their neighbors. The network may change, okay, so as long as it's moving as you go along. So this is all very nice and cool, but in this talk, to make things simple, I'm going to assume that all nodes communicate simultaneously and to get a pure synchronous algorithm. Why do we do this? Because first it's simpler, and also because then once all nodes communicate simultaneously, this means that simultaneously, for all I, you're going to replace theta I by an average of values of their neighbors. Okay? Again, W is 0, Wij is 0 if I and j are not neighbors. So if you put things together, you get essentially a linear operator, where you go from theta at time t minus 1 to theta at time t by just multiplying by a matrix, which is often called the gossip matrix. And since you have a linear recursion like this, you can unroll the recursion and obtain that after t steps, I get the power of my matrix W times some initial vector. And this initial vector is exactly the vector containing the values I wanted to average. Okay. So now, why is it nice? Because now you can analyze some linear recursions. And to make our life easier, I'm going to assume W is symmetric and W is stochastic. So W times the constant vector is equal to 1. So now if you assume this, then many things are known about that problem. First one, that the eigenvalues of that matrix are all between -1 and 1. The largest one is always equal of W. Okay. Set information throughout the graph. And the way to characterize this precisely is by simply recovering a result which is very similar to optimization. If I want to reach precision epsilon, okay, then what represents, to make things concrete, a small video, okay, so this is like in 2D, so I have like 100 nodes, 10 by 10, and I want to average those values, so 1 in the upper left corner, and -1 in the lower right corner, and the idea that as the algorithm progresses, I'm going to converge to 0, okay, this is here the average. So let's start. So as you can see, it's very slow. Okay, so after even like 100 iterations, then you're still very far from converging. Okay, so this is highlighting the fact that it is non-centralized, it is distributed, but still very slow. So I'm showing this because I'm going to make it faster. So just like remember this video for later. All right, so now I'm going to mix the gossip, which is how do I average like nodes in a graph with optimization. And we are clearly not the first one to consider that. There's a very long sequence of work, starting with Angela Nedick and Asuos Daglar in 2009, and a series of works, both from the control community and the machine learning community. And all of that mostly also for convex problems, and we are following the same steps. So first, a bit of lower bounds. So as I mentioned earlier, given the rules that are assigned to me about local computations and communications, there is some lower bound of complexity which we cannot beat. And this was achieved. This is like essentially in terms, again, of a number of guidance steps. Okay, so this will be related only to optimization quantity. So here, condition number, and the number of communication steps. And here, this will be both with condition number and the mixing time. So for the expert in the room, you maybe have noticed that when I was centralized, for the centralized algorithm, I had square root of kappa times delta. Okay? And it turns out that the mixing time is always bigger than the square of the diameter, with equality essentially if I have like an expander graph or something which is very, very well connected. And this essentially, you can have a link with the centralized case, which is always better. Okay, so in a sense, if you're willing to pay the cost of centralization in terms of number of iterations, you're always better than doing decentralized. But now, in the centralized case, the simplest algorithm was optimal. So I took the best algorithm for a single machine, okay, and then I made an effort to distribute it to have something which was logically equivalent. It was exactly the same thing, but done in a distributed fashion. It turns out that for the decentralized case, when you use gossip, it is not optimal anymore. The reason being that as you go along in the iterations, you need the gossip step to be more and more precise, okay? In the centralized case, they were all exact, so there was no worry about that. But in that case, you will pay an extra factor because you need to make the gossip steps more and more precise as you go along, as you get closer to convergence. Then the question is, if we can achieve it with the simplest algorithm, can we achieve it with something else? Okay, so this will be the only technical slide of the talk. Okay, so a small dual problem. I think before lunch, it's always nice to do it. Yep. This is that this is a lower bound saying that whatever you do, if you want to reach precision epsilon, you will never be able to do less than this.
But my model says like it has some bound on how much I can communicate each step, or is it a bound that I can only communicate one linear combination?
Or this is like the number of communications of full vectors.
So any vector.
Any vector. Yeah. All right. So let a small dual problem before lunch. So it's very nice. So I'm going to look at the finite sum. Okay, so this is a function I want to minimize. I remove the 1 over n because it was not fitting in the slide, but it should be there. Then, so the key here is to use the technique not due to us, but due to Jakovetic and colleagues, where I'm going to create local copies of my vectors. Okay, so here, theta I will be the copy of my parameter vector at a node number I. Okay? So I'm creating local copies, but of course, if everybody minimizes its own function, I don't get what I want, so I don't get the minimizer of the average. Okay? And one way to make sure that everybody is doing the same thing is to impose some constraints, okay, that all those vectors should be equal. And the beauty of this reformulation is the fact that I can only consider pairs of like local copies which are connected by a link. So whenever I and j are connected in the graph, I'm going to impose that the two values are equal. Okay, so if the graph is connected, this is equivalent to all of them being equal. Okay, so let's assume the graph is connected. And yeah, so this is the starting point. And now, since we have now a simple function, okay, totally separable, plus some constraint, we're going to use some Lagrange duality. And so introduce Lagrange multipliers. So lambda ij is a Lagrange multiplier associated with that constraint over there. And I'm going to add the constraint times the Lagrange multiplier and put it into the objective. This is classical Lagrange duality. And now I can invert the min and the max. Okay? And I'm not going to do all the computations. That would be a bit too tedious. But the key here is to realize the fact that as always, it's always the same when you do Lagrange duality. So the Lagrangian is typically simple with respect to the primal variables. It's totally separable in theta I. Okay, so at the end, the dual function will be a sum of functions, okay, which can be computed independently. And so at the end, the problem that I wanted to do, which was like minimizing this, is equivalent to maximizing with respect to Lagrange multiplier that function. Okay, this is classical duality theory. And what is amazing for that is that if you apply the simplest algorithm on that dual problem, so gradient ascent, then it turns out that this gradient ascent is exactly equivalent to one gossip step and one local and simultaneous gradient computations. Okay, so this is something which is very nice, and due to Jakovetic, is that we can use a simple algorithm, and this turns out to be equivalent to do local things and a gossip step. So why it is so nice? Because since we want to accelerate things, there are not many ways to accelerate algorithms. Okay, I know two. I know Chebyshev acceleration, next slide, and I know Nesterov acceleration. And whenever you want to go beyond those two, it's very difficult. So we have tried in this work to always reuse the two acceleration schemes that people are familiar with, Chebyshev and Nesterov. But here, as you can see, if we use Nesterov acceleration, and since you can show that this problem will have condition number kappa over gamma, you get the good number of communication steps, but you get an extra factor in terms of gradient steps. So it's not optimal yet. And to make it optimal, we need some acceleration, which I'm going to describe now. So this is classical when you have like some linear recursion like this. So this is my recursion. So theta t, okay, small mistake here, sorry, is the power of the matrix time theta 0. And what Chebyshev acceleration is doing, and this goes beyond gossip, this is a very classical technique in linear algebra, then it's going to consider linear combinations of those of the various vectors in the past. Okay, so I'm allowed to combine linearly theta 0 up to theta t. And the beauty here is that since theta k is a w power k times psi, I can form this matrix, which is a polynomial in the matrix w. Okay, so now whenever you combine linearly some past components, and and your recursion is a linear recursion, this is always true. So now the question is, what is the best polynomial? And as you can guess, the best polynomial is a Chebyshev polynomial, a rescaled Chebyshev polynomial. And so now you know the polynomial, but even better, you can do this recursion without having to store all the values theta 1 to theta 0 up to theta t. That would be like very time consuming. And at the end, what you can show that you get a second order recursion like this, where you do a gossip step. This is a classical gossip step, but you do a convex combination with a past iterates. Okay, so this is very simple to implement. And if you do this, first good benefit, you get the same form of acceleration as we get from for Nesterov acceleration. You replace the condition number here, 1 over gamma, by the square root of the condition number. So the 1 over the square root of gamma. So this is true in theory, but in practice, it's even nicer. So on the left, before acceleration. On the right, after acceleration. As you can see, this starts to be interesting. Yeah. So here, the condition number was around like, I think, 200, if I remember correctly. And now this is like a square root of 200, which is like much, much smaller. So now, if I combine everything, so if I do my dual ascent on my dual problem, and I replace gossip by accelerated gossip, then I get the optimal complexity, which I wanted. Okay, so now this is combining everything together, and now this works. All right. So this was the second part. This was if I want to minimize an average of function, okay, regardless of machine learning, what is the best I can do? And we did provide the optimal algorithm for that, optimal being if you're allowed to access gradients of the function and communicate with your neighbors, this is the best you can do. But the key here is that we have made no assumptions whatsoever regarding the functions themselves. And now we're going to make some assumptions and do better. Okay, so going back to that slide, now I'm going to assume that my functions here are also finite sums. Okay, so I have a finite sum here because each function is located in one node in one network, but each of them, if you do machine learning, is the training error on the data they have, that they have. So there I have a finite sum of finite sum. So now I can compare two things. I can compare what I would do with the previous slides. Okay, I have the optimal algorithm for distributed computing, so let's use it. Or I can also take all the data, put it on one machine, and apply the best single machine learning algorithm. So let's compare the two. So the first strategy, as I mentioned, is to put everything in a single machine, so I don't communicate Okay, I do it at the first time, and then I don't communicate. And the number of gradient steps is what I've described in one of the first slides. So since if I have n machines, each of them with m data points, if I put all of them together, I get n times m data points, assuming that all machines have the same number of data points. So now I can apply the bound that I had before to nm. Okay, this is nm plus square root of condition number times nm. And I can use the algorithms from before. Okay, so they were depending on some condition number as well, like for communication. But now in terms of gradient computations, if I'm counting the number of each local gradient computations, I don't have square root of kappa. I get square root of kappa times the number of functions that I have for every sum. So here m. So here, as you can see, when I take this MSD algorithm, the one from before, and I have a single machine, I'm back to gradient descent. Okay, so immediately, when using the previous algorithm, I cannot leverage the finite sum structure of every component, and I lose a lot. Okay, so you can check that here as soon you really need n number of machines to be big to recover from using a good algorithm in a single machine and using a good one, a bad one in the network. Now the goal is, can I make sure that to leverage the fact that I have a machine learning type function at every node of the network? And so just a summary, it's optimal, what we did before, but not adapted to machine learning. And very important here, when you go from 1 to 2 machines, you lose a lot. Okay, this is really not what you want to achieve. If you want to distribute computations, you want to make sure that if you go from 1 to 2, you don't lose much. And if you go from 1 to 10, you start to gain a lot. And from 1 to 100, you gain a lot. You don't want to wait for the number of machines to be too high to recover from using a distributed algorithm. And this is what we're going to do. And this is joint work with Adrien Hendricks and Laurent Massouillet. And it is adapted to functions which are finite sum. This is allowing partial asynchrony. Okay, so this is I'm going to allow updates to be done at different times. I still need partial asynchrony because I need to have a finite common clock. Okay, so once in a while I have to do things at a given time. Okay, so you can ask me more after the talk if you want. And what we achieve is essentially what we wanted to do, which is to make sure that if I take my algorithm with a single machine, okay, it works as well. Okay, so this is our complexity. Okay, again, m is the number of data points per machine, and n is the number of machines. And you can check that if n equals 1, there's a mistake there. If there's a single machine, then the two work the same. But if there are more than a single machine, okay, so if n tends to be large, then I reduce this to that. Okay, so if I have a very easy problem, okay, so this is the condition number is small, so those are the dominant factors, then I get a linear speedup. Okay, so I go from nm to m. Okay, I divide the time it takes by the number of machines. Whereas if I have hard problems, very ill-conditioned problems, I get a square root speedup. So how does it work? Okay, so it's based on a very simple principle, but as most simple principles, it's easier once you see it. Okay, and this is a nice contribution of Adrien Hendricks. So we start with our finite sum of finite sums, okay, like this. So we assume that we have like 3 nodes to make things simple. Okay, so 3 functions. Each of the functions is a finite sum. And what he did is to create a virtual graph, okay, with all functions are attached to a single node. Okay, so this is the original graph, okay, and you put the regularizers in it, and you create like attached to each of those nodes virtual nodes, okay, where you put all the components of the finite sums associated with that function. Okay, so here is the function f1, and we put all the components. Here 3 components to make things easy. And now what you have is you have a network. Okay, so those are nodes which are actual nodes. Okay, going to communicate over a network, and the node here, these nodes in the dashed are virtual nodes that will not do any communication. As you can check, if you take the sum of all the functions over the graph, you recover the exact cost function. Okay, so we are still optimizing the same thing. And now we're going to use the same technique as what we had before, which is to create some dual problem, okay, and do some ascent algorithm on the dual problem. And here we're going to not to do gradient ascent, we're going to do coordinate ascent. So this means that, and remember that the variables are attached to edges, so that every time step we're going to select an edge at random, okay, and do some optimization about that edge. Okay, so sometimes this is a virtual communication, and sometimes this is some actual communication. And if you do this, then you achieve what I said in the earlier slide, that you get the complexity which I described. So this is like the story is a bit more complicated because you have to be careful in the way you select, you sample your edges, and you have to use non-uniform sampling. And if you want to know more, the paper has all the details. All right, so how does it work? So we started with very simple data here. Okay, so logistic regression with 10,000 observations and like in small data. Okay, and the idea here was to compare the situation where you have a small number of nodes. Okay, and here the number of computers. So on the left, 4, quite small, and on the right, 100, which is a bit bigger. So this was run on our cluster in the lab. And so there are various techniques. So ours is a blue one. Okay, so this is a new technique that we designed. In green, this is the optimal single machine algorithm, where I take my data, put it in a single machine, and run the best thing that I know, which is accelerated variance reduction. Here, point saga. And when n and those are the other techniques which are using distribution. So MSDA is the one I described, which is not leveraging the finite sum structure of each component. Okay, it's not doing very well. So as you can see, when I use 4 machines, all the techniques which are supposed to be good for distribution are in fact really bad. Okay, and we are barely do better than the single machine algorithm. Okay, so here, with a small number of machines, it's not too bad, but it's not great, and we are robust, but do a little bit better. But now if you go to a bigger number of machines, so now we still have a very nice behavior. The single machine one in green is doing really bad, and the distributed ones are doing also a bit better, but here, in our scenario, we still do much better. A bit bigger, okay, so a bit more observations and a bit bigger data, and same cluster, okay, and here we were not even able to run all techniques because it was too hard, too slow to implement. And again, you see the nice linear convergence behavior. Okay, this is something that the log factor which I presented earlier, okay, so in the semi-log plot, this is time in the x-axis, and this is distance to optimum in the y-axis. So you see a line, so this is just confirming the linear convergence of the algorithm. Well, so to conclude, in this talk, I've tried to present a way to distribute the fastest single machine algorithm. Okay, so the idea is that when you go from 1 to more machines, you want to do at least as well as with a single machine. And what we achieved is that if you have n machines and n observations per machine, then we went from this complexity for the single machine. And again, this is the best algorithm in a single machine. And what we are obtaining is something where there's a reduction in the time number of gradient steps, okay, which is linear if you have an easy problem with a small condition number, and something which is a square root of n improvement if you have hard problems. So several questions that are natural. First, can you be fully asynchronous? Okay, so this is something that we are currently exploring. Second, how does it work for convex problems? Okay, so at the moment, since we're using a dual formulation, we cannot apply it to non-convex problems. It's not even well defined. So Adrien is working hard at the moment to make a primal-only version of those algorithms, and has almost achieved it. This is what he claims, and I trust him, of course. And so try to go beyond convex problems, so primal-only algorithms. And then, is this optimal? Okay, so when you do theory of optimization, you're only happy if the lower and upper bounds are matching. Here, I'm providing some upper bound of complexity by providing you with an algorithm. Is it the best you can do? And again, Adrien has good arguments to show that this is indeed optimal. And at the end, so as you may have noticed, there is not a lot of real experiment at the moment. And this is what Adrien is doing at the moment at Microsoft in Redmond, trying to see if this can be made to work really well on the actual cloud platform. Thank you for your attention. That's a very good question. We didn't look at it, but it was not our purpose to prove privacy. But clearly, we could imagine that to add some layer to make sure that we cannot reconstruct the gradients. At the moment, I'm pretty sure that you can reconstruct parts of the inputs by looking at gradients, for sure.
And the second is about the ADFS algorithm.
They are sharing like parameter vectors. So which is d-dimensional. Yeah. So we have, yeah.
Okay, and the norm in the function f, the norm of the grounded data, why is the fact that there is a sigma there?
Oh, so here, so on here, so for algorithm to work, we need to have this formulation with a finite sum plus some regularizer. So anyway, whenever you run like for machine learning, you always use some regularization. So here we impose that we have a square norm regularizer, and typically sigma I is of the order of 1 over n, typically. Okay, this is the reason why you get a big condition number is because sigma I is typically pretty small. Okay, we need for all the dual formulations, typically you need to add some regularizer to make them work, and we are following the routes that similar route.
Be careful not to, let's say, send messages that we just received so that basically, and there's a way to avoid that by non-backtracking.
Yeah.
So Giri don't seem to be affected by
I think this is the role of acceleration. So if you don't do acceleration, you do get this like bad behavior where it takes a long time to diffuse information. Okay. Essentially, the acceleration is like building a fake graph, which is like much better. Okay, so this is one way of seeing it is that acceleration builds a new graph where things don't backtrack as much. It's not equivalent, but this is the way I see it. Yep.
So you mentioned that doing the same thing that also takes test error into account, generalization, would be like a second talk.
That would be
1 minute summary, and
no,
when do you come back to pick that talk?
that's very. It's a talk about work which I have not done yet. Okay, so I can give you the highlight if you want. So essentially, you replace. So if you take that slide, let's take the first slide because this is what's happening. So now those complexities are for like training error. If you go to testing error, first you're going to lose all the logarithmic dependence. Okay, you cannot do better than 1 over n when you have n observations and you want to do test error development. And then for that, the best algorithms are typically like stochastic gradient descent with a single pass, okay, and with typically a big step size and averaging. And if you want to use that, plus some distribution, like gossip type things, then we should expect to obtain things which are similar, essentially like linear speedup or a bit worse for test error. But at the moment, it's not done yet, so I cannot promise anything, but this is the goal.
But I mean, there's also fundamental difference if you want to optimize test error, that you want overfitting and so on.
No, but the way, there are two kinds. The way to avoid overfitting is by doing a single pass over the data. Okay, so this is a classical way to avoid overfitting. And second, when you do SGD, okay, so something I didn't insist so much on is a distributed case. It's often called a consensus optimization, okay, meaning that functions may tell you different things, and you want to read some consensus among the machines. If now all machines are sampled from the same source, then it's not really a consensus. They all try to help you. they all have some noise, and you want to benefit from the noise reduction by having multiple machines. Okay, so what we are planning to do is more to consider that case where all machines are helping each other, and not one machine trying to do something different from the other machine. And then these should get some linear speedups. If the machines try to drive you to different places, it's going to be much more difficult.
Can you comment on the robustness for your problems with respect to delays, for example?
Oh, that's-
or the information loss creation?
That's a very good. That's a very good question, and we have not explored it yet because in practice we can test it, okay? But in theory it's quite hard. But this is on the to-do list for Adrien for the next rest of his PhD.
So in practice, I imagine regular gossip is pretty robust to like delays, but
Yeah, yeah.
accelerated not. Is that-
Oh, acceleration should be highly non-robust.
Okay, so that would
So it's known that, so acceleration, like Chebyshev acceleration, this sort of acceleration, is known to be non-robust to errors. Okay, so if you have errors, your acceleration may diverge. So it's known for conjugate gradient. It's less robust to errors than regular like iterations, and here it should be the same as well. Although we have like other ways of accelerating with a different student that could be robust to that. Yes, no? No? Yes. He doesn't know yet, but he's going to be robust. Oh, wow.